Hello. Today we are moving to the second part of section 12.1. Section 12.1 is formal languages and regular expressions. This is chapter 12, which is regular expressions and finite state automata. All right. In this part, we are going to talk about the language defined by regular expressions. All right. This section, this part of the section doesn't have lot of problem solving. It is mostly details like essay reading. Okay, mostly this part of the section mostly has details, so anybody can read and understand. All right. So let me read it from the first slide. One of the most useful way to define a language is by means of a regular expression. Okay, means of a regular expression. A concept first introduced by Klein. Given an alphabet sigma, the following are regular expressions over sigma. All right, so these are the regular expressions. First regular expression, the base, here we define the base, which consists the empty set and string of length 0. This is empty set. All right, and then lambda, which is strings of 0 length, and each individual symbol in sigma are regular expressions over sigma. All right, and the part 2 is recursion. If R and S are regular expressions over sigma, then the followings are also regular expressions over sigma. The first one is R times S. The second one is R slash S. That the last one is R asterisk. Okay, here we define them. RS means this denotes concatenation of R and S. Okay, concatenation of R and S, and then R star denotes concatenation of R with itself any finite number of times. Okay, so you can concatenate R with any number of times, and then finally this R slash S denotes either one of the strings R or S. All right. So when we discuss an example, you can understand this very well. The regular expression R asterisk is called the clean closure of R. There are some restrictions. So these are the restrictions. Nothing is a regular expression over sigma except for objects defined in 1 and 2 above. Okay, so in order to be a regular expression, it should be explained in 1 or 2 above. All right, what we discuss in 1 or 2, first one is the base. We define the base, or it might be either base or the recursion. Okay, so those are the only two possibilities for a regular expression. Example 12.1.5. Add parentheses to emphasize the order of the precedence in the following expression. Okay, the expression is A, B asterisk slash B asterisk A. And part B of the problem, use the rules about order of precedence to eliminate the parentheses in the following expression. So this is the expression. Okay, first case you have to put the parentheses. Second case you have to eliminate the parentheses. Okay, so these are the two problems here. It's very easy. As I explained, this part of this section is very easy. First, you have to put the parentheses, which is actually given here. First, you put parentheses for B asterisk, and then you separate A and B asterisk. All right, and then you put the slash, then separate B asterisk, and then separate B asterisk A. Finally, you put this parenthesis for everything. All right, so you can pair the parentheses if you need. This goes with that, and this goes with that, that goes with this, and finally this goes with that. Okay, these are the way the parentheses are set. In the next case, you have to eliminate the parentheses, so you can eliminate unnecessary parentheses. First of all, you have to understand the order of the parentheses. You have this for that, and then you have that for that. Okay, and then you have this for that, and again this for that, and finally you have this for that. Okay, that's how the parentheses are set. You can eliminate unnecessary parentheses. Of course, you can eliminate the blue parentheses, which is not important, and then you can eliminate the parenthesis for A, which is the pink parenthesis, and then you can eliminate this green parenthesis. All right, so if you just eliminate those parentheses, what you get is this. You have you have only one pair of parentheses, that is between A, that's actually this pink one. All right, that's the only one you have to put. You can remove the rest of them. Okay, rest of them are not meaningful actually, so you could remove the rest of them. Okay, I forgot that you could remove. Give me a second. You could remove this too. Remove that too. All right. So that's how you put parentheses. Given a finite alphabet, every regular expression over the alphabet defines a formal language. The function from regular expressions to formal language is defined recursively. All right, so it is given in this table. For any finite alphabet sigma, the function L that associates a language to each regular expression over sigma is defined by 1 from 1 to 3 below. For each such regular expression R, LR is called the language defined by R. Okay. The first point, we define the base, that is L of the empty set is just the empty set, L of lambda is just lambda, L of A is just A. Okay, so these are the definitions. That's how they are defined. All right, so you have to keep them in mind. And then recursion, this is the base, and then you have the recursion. Recursion, if L of R and L of R prime are languages defined by the regular expressions R and R prime over sigma, then the first part is language R times R prime equals LR, L of R times L of R prime, and then you have L of R slash R prime equals L of R union L of R prime. Third, L of R asterisk equals L of R, then everything to the asterisk. L of R and the asterisk. All right. So these are the definitions. You don't need to worry about them. So only thing is you have to keep them in mind. And then there's the restriction. The restriction says the function L is completely defined by 1 and 2 above. Okay, so all the things here defined by either 1 or 2. That's the restriction. All right, so let's move to the next example. You can understand this very well. All right, here sigma is a comma b, which is the alphabet a comma b, and consider the language defined by the regular expression a slash b asterisk. Use the notation to find this language and describe it in words, right? So first of all, you have to find the language. That means L of a slash b asterisk. Now we can use these properties that you already learned. So you could use these properties to work on that. All right. Here you have asterisk, because you have an asterisk. You could use that condition. Okay, you could use that condition. What this condition says? Either you can bring that asterisk outside, or you can keep the asterisk inside. All right, for both are same, it's equal sign. Either you can keep the asterisk inside of the parentheses, or you can take outside from the parentheses. All right, so here what we do is the asterisk is inside, so we'll bring it outside. All right, and then this part is L of a slash b, which is right here. So you can replace that by union. See, you can just replace this slash by union. So you just write it L of a union L of b. All right, L of A is A, because that reason you could just put A here, and L of B is B. Okay, and here you have A union B. That's the next step. A union B is actually A comma B. You can just put A union B means A and B, so that's A comma B, and then outside you have the asterisk. Okay, the meaning of this one is, the meaning of that one is the set of all strings of A's and B's. All right, so if you just go back and check the meaning of asterisk, which is right here, the meaning of that one is right here. R asterisk denotes the concatenation of R with itself any number of times. You could concatenate R any number of times. That's the meaning of asterisk. All right, so go back. A set of all strings of A's and B's. That's the meaning of asterisk. So you can concatenate A and B any number of times you need. That means the set of all the strings of A's and B's. All right, so let's go to the next slide. Here the next example. Your alphabet is 0 and 1. Use the words to describe the language defined by the following regular expressions over sigma. The first one is 0 asterisk 1 asterisk slash 1 asterisk 0 asterisk. Okay, so it is defined right here. So let me read that. This is the strings in this language consist either of a string of zeros, okay, followed by a string of ones. This means you can just have any number of zeros at the beginning, and you can have any number of ones next. Okay, so it will be something like 0 0 0 0 and then ones, or you have few ones or followed by zeros. So that is the meaning of that. That's one of the example. Okay, in the next case, you should have 0 at the beginning, then you can just have 0 and 1, 0 and 1s. You can just switch 0 and 1s, but at the beginning there should be a 0. Okay, the meaning of this dash means you can either have 0 or 1, anything. Okay, 0 and 1, you can just alternate if you need. And the meaning of this asterisk is you can have many number of times, you can have that number many number of times. Okay, so let me read that. This is the first part. The string in this language consists either of a string of zeros followed by a string of ones, or of a string of ones followed by a string of zeros. However, in either case, the string could be empty, which means that lambda is also in the language. Next part B. The strings in this language have a start with 0. I explained it should have this start 0. Okay, it should have this start 0. The 0 may be followed by any finite number of zeros and ones in any order. Thus, the language is the set of all strings of zeros and ones start with 0. Okay, that I already explained. All right, so let's move to the next example. Example 12.1.10. In A and B, determine whether the given regular expression define the same language. If they do, describe the language. If they do not, give an example of a string that is in one of the language but not in the other language. All right, so let's move to the first part. Note that because the null string lambda has no characters, when it is concatenated with any other string x, the result is just x. That's true, right? X times lambda equals lambda times x equals x, because lambda is a string with no length. All right. Now, language a slash lambda asterisk is the set of a string formed using a and lambda. That's true. It's using either a or lambda in any order. Okay. A lambda is something like a lambda, lambda a, something like that. So let me write this. This is a lambda, lambda a, lambda a, lambda a, like something like that. You can repeat lambda and a in any order. Okay, then lambda has no length. That means finally you get a. Okay, so you can just omit lambdas. In this case, example is any number of a's, like a. Okay, so if you put 6 a's, then this will be equal to that. Okay, so these two will be equal. All right, that's what I'm explaining here. This is the same as the set of a string consisting of zeros or more a's. Thus, that equals this. So they are equal for the first case. Okay, both languages are equal. Go to the second part. Meaning of that is you can sorry, not that. The meaning of this one is you can repeat any number of zeros and then after that any number of ones, something like that. Example would be like that. Here you are just repeating zeros and ones. Okay, 0 1 0 1 0 1 0 1. So you can see they are not equal. Here they are not equal. All right. The two languages defined by the given regular expressions are not the same. 0 1 0 1 is the second language but not the first. Alright, so I explain everything here. So let's move to the next slide. Now in the next slide we are going to talk about the practical use of regular expressions. This part is mostly description, so you can just read and understand. So let me read it for you. Many applications of computers involve performing operations on pieces of text. For instance, word and text processing programs allow us to find certain words or phrases in a document and possibly replace them with others. All right. A compiler for a computer language analyzes an incoming stream of characters to find grouping that represent aspects of the computer language, such as keywords, constraints, identifiers, and operators. And in bioinformatics, pattern matching and flexible searching techniques are used extensively to analyze the long sequences of the base pairs A, C, G, and T that occurs in DNAs. All right, so these are mostly descriptions, so I'm reading them. No math here, right? Just descriptions. Regular expressions provide an extremely useful way to describe a pattern in order to identify a string or a collection of strings within a piece of text. Regular expressions make it possible to replace a long, complicated set of if then else statements with code that is easy both to produce and to understand. The computer language Perl has a particular powerful implementation for regular expressions, which has become a de facto standard. The implementation used in Java, Python, and .NET are similar. A number of shorthand notations have been developed to facilitate working with regular expressions in the text processing. All right. Let's go to the next slide. When characters in an alphabet or in a part of an alphabet are understood to occur in a standard order, the notation is this. The notation is beginning character, then the ending character, and a square bracket. It is starting with a square bracket, beginning character, dash ending character, end with another square bracket. Is commonly used to represent the regular expressions that consist of a single character in the range from the beginning to the end character. It is called character class. Alright, let's move to the next example so you can understand that thing. This is example 12.1.11. People often write dates in a variety of formats. For instance, in the United States, the following all represent the 5th of February of 2050. All right, so these are the representations. People write the dates in different formats. Write a regular expression that would help check whether a given string might be a uh, valid date written in one of these forms. You have to write a regular expression that represents all these four forms. All right, it is here. The language defined by the following regular expression consists of all strings that begin with one or two digits. It can begin with one or two digits. Here it's one digit, here it's two digits. Followed by either a hyphen or a slash. It can be a hyphen or a slash. All right. Followed by either one or two digits. Again, it can be one digit or maybe two digits. Followed by either hyphen or a slash, followed by four digits. Again, hyphen or a slash, and followed by four digits. All right. So this is these are the characteristic of those four forms. All right. Now this is the regular expression we have. It says 0-9. That means this represents numbers from 0 to 9. I'm sorry, 0 to 9. And then this represents one or two numbers in the previous format. One number or two numbers. One number or two numbers, and then again here this means dash or hyphen. I'm sorry, hyphen or dash. And again 0, number between 0 and 9, and one or two places are filled with such that, and 0 to 9 numbers, and then 4 places are filled. This means the meaning of that is four numbers. All right. All valid dates of the given format are elements of the language defined by this expression. But the language also includes strings that are not valid dates. All right. For instance, if you just write 954 1974 is in the language, all right. So this is in the language. It has two numbers and backslash, and two numbers backslash, and four numbers. Okay, so this is a valid valid by the language. This is valid by the language. All right. What I'm saying is this is in the language but not valid. This is in the language. This is in the language. This is in the language, but it is not valid date because the September does not have 54 days, and 38 backslash 12 backslash 2184 is not valid because there's no 38 months. Okay, now you can understand what is given here, which is very straightforward. Yes, that is the end of this section. Thank you very much.